everyone. Today we are going to be talking about calculating gravitational potential energy, or GPE. So consider that you have an object that is being held above the surface of the Earth. We know that if we release this object, it will fall to the surface of the Earth. And the reason that that happens is because the object has gravitational potential energy, and that is what we're going to be diving into a little bit more today. Okay, so we know about work. Work is a force times a displacement. Now in this case, the displacement is how high that object is above the surface of the Earth, which we will call its height. So what about the force? Well, this force is going to be the force due to gravity, and we know thanks to Newton that the equation for this force is Gmm over r squared. Now in this case, the g is the universal gravitational constant, big M is the mass of the Earth, and little m is the mass of the object. And r is just the distance between the center of masses of the objects. And in this case, that's just the radius of the Earth. And this negative sign here means that the force of gravity is attractive. It's always trying to pull two bodies closer together. Now this particular combination is so common that it actually gets a name of its own, and that is little g, or the acceleration due to gravity at the surface of the Earth. Now, because all of these things are constant, the radius of the Earth, the mass of the Earth, and the universal gravitational constant, g at the surface of the Earth is also constant, and it has a value of 9.8 meters per second squared. Note that the unit here is a unit of acceleration. Now this should also make sense because if we go back to our friend Newton, we know that he said in his second law, force equals mass times acceleration. So the force due to gravity is the mass on the object times acceleration, and so in this case the acceleration is just given by g, and again, negative means that it's going to be directed downwards. Okay, so going back to our object, how does this concept of work translate to the gravitational potential energy? Well, the work done by gravity moving the object from here to here is given by the force times the displacement. And based off what we just discussed, we know the force is going to be the mass of the object times the acceleration due to gravity, and the displacement is going to be the height of the object. So the fact that when this object is at a height h above the surface of the Earth, and if we let it go, it will have this work done on it, means that it has a capacity for gravity to do work on it. And that capacity for gravity to do work is what we call the gravitational potential energy. So we can quantify the gravitational potential energy by how much work gravity could do on this object, which we know if we let it go and let it fall all the way to the surface will be mgh. And so we quantify the gravitational potential energy of an object above the surface by mgh. Let's go ahead and do an example. Let's say that we have a cliff diver standing at the top of a cliff above some water. This cliff is 10 meters tall, and our cliff diver has a mass of 75 kilograms. So as she is standing at the top of the cliff, what is her gravitational potential energy? Well, we can use this equation to solve for it. So we know that it is going to equal mgh, and her mass is 75 kilograms. G, we said, is a constant, that is 9.8 meters per second squared. And h is her height above the surface, and sea level is going to be the surface of the Earth, so we know that this is 10 meters. Now if we calculate that out, we get 7,350 kilograms meters squared per second squared. Now this unit is kind of a mouthful, and so we actually have another equivalent unit that we can use that's just called a joule. So this is actually just equal to 7,350 joules. Okay, so let's say that our intrepid cliff jumper decides to actually take the plunge and jump off the cliff. So what is her gravitational potential energy now? Well, again, we can go back to our equation, and this time 0 joules because we're multiplying by 0. Gravity has in fact done work on our cliff jumper, and we know that work is equal to the change in kinetic energy. And we also know this from conservation of energy, because at the top she has 0 kinetic energy and all this gravitational potential energy, and at the bottom she has 0 potential energy, and so it must have been converted to kinetic energy via work. So if we know the formula for kinetic energy, which we do, it's 1/2 mv squared, we can actually do something pretty interesting here, which is solve for her velocity as she enters the water. So to do this, we can set her kinetic energy at the bottom equal to her gravitational potential energy at the top. We can just write mgh because we know that's the expression for gravitational potential energy. And something really interesting here that happens is that your mass actually cancels out because mass is involved in both of these energies. So now if you finish solving through for velocity, you'll find that v equals the square root of 2gh. And so in fact, this does not have any mass dependence at all. Now if we want to find an actual number here, we can plug in our values. We know 2 times 9.8 meters per second squared times 10 meters, and take the square root. Let's double check our units. Now we have meters squared per second squared, but we're going to take a square root, so we'll end up with meters per second, which is good because that's a velocity. Her speed when she enters the water is going to be 14 meters per second because gravity has done work on her and all of her gravitational potential energy has been converted into kinetic energy. Now it might sound a little crazy that the velocity entering the water does not depend at all on her mass, but we can actually see this in some real data. Here on the left, they're just showing a camera of the diver entering the water from a 10-meter tower. And here on the right, they're actually showing the velocity of the diver over time after entering the water. So t equals 0 is the moment which they enter the water. And this axis here is their speed. And so we can actually see that they enter the water right at 14 meters per second. So that is in fact what we expected. So our math worked out, which is pretty cool. So today we talked about gravitational potential energy, and we derived an expression for it, which is mgh, where m is the mass of an object, g is the acceleration due to gravity at the Earth's surface, and h is the height above the surface of the Earth. We said that this gravitational potential energy is the capacity for gravity to do work on an object. And we said that this gravitational potential energy can be converted to kinetic energy. We also did some sample calculations and looked at an example of real data. I hope you enjoyed and learned a little bit of something.